In this video, we'll talk about computing derivatives of logarithmic functions. We can differentiate the natural logarithm function using the fact that the natural logarithm is the inverse of the exponential with base e. The natural logarithm rule tells us that the derivative with respect to x of the natural logarithm is equal to 1 over x. This is something that we can prove using the chain rule. Our goal is to compute the derivative with respect to x of ln of x. So how are we going to do this? Well, we use the fact that the natural logarithm is the inverse of the natural exponential. So we have that e to the ln of x is equal to x. And then we differentiate both sides. The derivative with respect to x of e to the ln of x is equal to the derivative with respect to x of x. And this term on the right is just the derivative of x with respect to x, so that's just 1. So whatever this derivative on the left is, it has to ultimately be equal to 1. But the derivative on the left is the derivative of a composition, so we can use the chain rule. We have e to a thing, so the derivative of e to a thing is e to that thing again. But then we have to multiply by the derivative of whatever that thing in the exponent is, which in this case is ln of x. And we know that this has to equal 1 ultimately. And now we take a look at this expression here, e to the ln of x. Well, e to the ln of x, that's just x, using the cancellation laws. So we have that x times the derivative with respect to x of ln of x is equal to 1. And now, if we just divide both sides by x, we'll have the desired result, which, of course, is that the derivative with respect to x of ln of x is equal to 1 over x. That's our natural logarithm rule. There is a more general rule for a more general base. The derivative of log base a of x is 1 over x natural logarithm of a. Notice that there's suddenly a natural logarithm here. There are different ways to prove this, but perhaps the easiest way is to just simply use the change of base formula for logarithms. So log base a of x is equal to the natural log of x divided by the natural log of a. And this is exactly where your log base a shows up. This natural log of a is the same as this natural log of a. Because if we differentiate log base a of x, this is the derivative with respect to x of, using the change of base formula, ln of x over ln of a. And now we just factor that ln of a out, just using the constant multiple rule. So it's 1 over the natural logarithm of a times the derivative with respect to x of ln of x. But we know what the derivative with respect to x of the natural logarithm of x is. That's 1 over x. So what do we have? We have 1 over ln of a times x. And that's exactly the same thing, just in the opposite order. But you're allowed to multiply in the opposite order. So this gives us a general logarithm rule, which tells us how to differentiate logarithms with any base. Let's compute some examples. So for our first example, we're going to find a formula for the derivative dy dx if y is equal to x times ln of x. In that case, dy dx is equal to the derivative with respect to x of x times ln of x. This is a product, so we wish to compute the derivative of this product using the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. And these derivatives we know how to compute. The derivative of x with respect to x is 1, and the derivative of the natural logarithm with respect to x we now know is 1 over x. So our derivative dy dx is equal to 1 times ln of x plus x times 1 over x, which is ln of x plus 1. And that's the value of our derivative. Let's do another example. Find a formula for dy dx if y is equal to the natural logarithm of the absolute value of x. So notice we have some absolute values there. What this effectively does is increases the domain. ln of x has domain the numbers from 0 to infinity, because you can't put in a negative number into the natural logarithm, or 0. ln of the absolute value of x increases the domain to include the negative numbers. So this has domain negative infinity to 0 union 0 to infinity. We still have to exclude 0. If we were to graph this function, what would it look like? Well, when x is positive, we just have the usual natural logarithm of x. When x is negative, we look at the absolute value and then compute the natural logarithm of that, and we'll end up with the mirror image. The natural logarithm of the absolute value of x is equal to, well, if x is positive, then it's just the natural logarithm of x. But if x is negative, then it's the natural logarithm of the opposite of x, if x is less than 0. Now, don't be fooled by this negative sign. We're not looking for the natural logarithm of a negative number. X is already negative. So don't think of this as minus x or negative x. This is the opposite of x. X is already a negative number, so the opposite of x will be a positive number. So this is well defined. And when you put a negative in front of your argument, that has the effect of flipping the curve. So that's why we have this symmetry about the y-axis. Indeed, this makes ln of absolute value of x an even function. Okay, well, what we want to do is compute the derivative. This function is certainly not differentiable at 0, but it is differentiable everywhere else. We already know that if x is positive, then we have the derivative with respect to x of ln of the absolute value of x is just equal to the derivative with respect to x of ln of x, because the absolute value of x is just x when x is positive. And we know what this derivative is. It's 1 over x. So when x is positive, the derivative of ln of absolute value of x is 1 over x. The real question is what's going to happen when x is negative? What's that going to look like? If x is negative, then we're looking at the derivative with respect to x of ln of the absolute value of x. But now x is negative, so we write this as the derivative with respect to x of ln of the opposite of x, because x is negative. And so now we have a composition. It's ln of a thing. So if you're computing the derivative of a composition, ln of something, it's going to be 1 over that thing, and then we're going to have to multiply by the derivative with respect to x of whatever that thing is. Now, what is that thing in this case? Well, it's the opposite of x. So you just put an opposite of x here and an opposite of x here. But the derivative with respect to x of the opposite of x is negative 1. So that means we have 1 over the opposite of x times negative 1. And that's just going to give us 1 over x. So it turns out that regardless of whether x is positive or negative, the derivative with respect to x of the ln of the absolute value of x is going to have the same value, namely 1 over x. Let's do another example. Find a formula for dy dx if the natural logarithm of 1 plus y squared is equal to x plus y. Well, this is an implicit relationship between x and y. We're not able to solve for y explicitly as a function of x. So what that means, we're going to need to use implicit differentiation. So we simply differentiate both sides. So we're going to have the derivative with respect to x of ln of 1 plus y squared is equal to the derivative with respect to x of x plus y. Let's start by looking at the derivative on the left. This is a composition. It's the derivative with respect to x of ln of a thing. So we want to compute the derivative of ln of a thing. The derivative of ln of anything is just 1 over that thing. So in this case, it's 1 plus y squared. But then we have to multiply by the derivative with respect to x of whatever goes inside there. And of course, the thing that goes inside there is 1 plus y squared. So this is our inside function is 1 plus y squared. Now that's on the left. What about on the right? Well, we have the derivative of a sum, so we can differentiate that term by term. So we'll have the derivative of with respect to x of x plus the derivative with respect to x of y. Now both of these are easy to compute. The derivative with respect to x of x is just 1, and the derivative with respect to x of y, well, I guess it's not right to say that it's easy to compute because that's what we're trying to find. This is unknown to us, but it's just dy dx. Okay, well that's the right side. What about the left side? Well, we have this 1 over 1 plus y squared, but now we want to multiply this by the derivative of 1 plus y squared. So this is going to be the derivative with respect to x of 1 plus the derivative with respect to x of y squared. And all of this is going to be equal to 1 plus dy dx. Well, the derivative with respect to x of 1, that's just 0. And here we have the derivative of y squared with respect to x. So we have something squared, so we use the power rule. So it's going to be 2 times y to the 1, but then we have to multiply by the derivative of y with respect to x. Keep in mind that this is really just another application of the chain rule. We have something squared, something raised to the second power. So if you differentiate that, you're going to have 2 times that thing raised to the 1 power times the derivative of that thing with respect to x. So it's really just the chain rule. Let's put all of this together. We have 1 over 1 plus y squared times 0 plus 2y dy dx, and this is equal to 1 plus dy dx. Now ultimately the thing that we're trying to do is solve for dy dx. We were asked to find a formula for dy dx, so that's what we're trying to do. So let's get rid of that 0. So this is just 1 over 1 plus y squared times 2y dy dx equals 1 plus dy dx. Now we want to get these dy dx's all together on the same side. So I'm just going to subtract this dy dx over to the other side, and then we'll have 1 over 1 plus y squared times 2y dy dx. So I'm going to subtract dy dx, and that's equal to 1. So if I just color code this dy dx is that dy dx. We just subtracted it over to the other side. So now we're going to factor out the dy dx, and the thing that's left behind will be 2y over 1 plus y squared minus 1, and this will equal 1. So this 2y, I've just written it in the numerator. I've just combined these two terms to 2y over 1 plus y squared, and here's a minus 1. So the next thing I'm going to do is I'm just going to divide by that term. So we'll have that dy dx is equal to 1 over 2y over 1 plus y squared minus 1. Now, it's certainly possible to simplify this. I don't know that I think it's necessary, so I think we'll just leave it like that. Let's try another example. This one seems a little bit more complicated. The derivative with respect to x of ln of x squared times the square root of 1 minus x over 1 plus x. So we can compute this derivative using all of the rules that we have with a very heavy application of the chain rule. The derivative of ln is 1 over a thing. So we can just say 1 over this expression times the derivative of this expression. Okay, well that's going to be a product rule, x squared times the square root of a thing. But then this thing is the square root of a quotient, so we have to use the chain rule to write this as 1/2 of the quotient to the negative 1/2, and then we have to multiply by the derivative of the quotient using the quotient rule. Okay, well that is a lot of work. However, we can use the properties of logarithms to simplify this a lot, because remember what the properties of logarithms do. They turn multiplication into addition and division into subtraction. So this is going to be the same as the derivative with respect to x of, and now we're just going to use the properties of logarithm with that logarithm right there. So the first thing that we're going to do is we're going to change the multiplication into addition. So this is going to be ln of x squared plus ln of, and so this is 1 minus x over 1 plus x, and it's all with the square root. But I'm going to just rewrite this as to the 1/2 power. And why am I going to do that? Because another one of the properties of natural logarithm is that it enables us to take the exponents out of the exponent and put it in front of the logarithm. So we can take that squared out, and we can also take out this 1/2 and put that in front. So we can take this x squared out there and this 1/2 out there. So we haven't even computed any derivatives yet. This is the derivative with respect to x of 2 times ln of x plus 1/2 times ln of a quotient. But remember that logarithms turn division into subtraction. So this is going to be the derivative with respect to x of 2 times ln of x plus 1/2 ln of 1 minus x minus 1/2 ln of 1 plus x. Let me just fix this ln here. So that's a natural logarithm. This 1/2 and this 1/2 are that 1/2. I've rewritten ln of this quotient as ln of 1 minus x, the numerator, minus ln of 1 plus x, which is the denominator, and then I just distributed that 1/2. So now we can differentiate term by term. So this is going to be 2 times the derivative with respect to x of ln of x, just taking the constant out using the constant multiple rule, plus 1/2 times the derivative with respect to x of ln of 1 minus x, minus 1/2 times the derivative with respect to x of ln, that's supposed to be an ln 1 plus x. So here we have the derivative with respect to x of ln of x, that's 1 over x. This one is the derivative with respect to x of ln of 1 minus x. So this is actually a composition where the inside function is 1 minus x. So this is going to be the derivative of ln of a thing is going to be 1 over that thing. But then you have to multiply by the derivative with respect to x of whatever was inside there, which was 1 minus x. So you have 1 minus x as our inside function. For this last derivative here, it's the same idea. It's ln of a thing. So the derivative of ln of a thing is going to be 1 over that thing times the derivative with respect to x of that thing, which in this case is 1 plus x. So our inside function is 1 plus x. Now these derivatives are things that we can compute. The derivative with respect to x of 1 minus x, that's equal to a negative 1. It's 0 minus 1. And the derivative of 1 plus x is 0 plus 1. So that's going to be equal to positive 1. So that tells us that our final answer is going to be equal to 2 times 1 over x plus 1 half times 1 over 1 minus x times a negative 1 minus 1 half times 1 over 1 plus x times a positive 1. And we can simplify this. This is 2 over x minus 1 over 2 times 1 minus x, and then minus 1 over 2 times 1 plus x. And we just had to sneak it in the corner, but that's our answer right there. So we could have done this just using a lot of applications of the chain rule, the product rule, and the quotient rule, or we could use the properties of logarithms to simplify this significantly before actually computing the derivative. And then once you do that, all of the derivatives are quite straightforward. You can actually introduce a logarithm into a problem in order to make the computations easier. This is a process known as logarithmic differentiation. So for example, here we have y is equal to the square root of x times sine of x squared, so maybe we should write it like this, divided by this polynomial, 1 plus 3x squared plus x to the 4. And what we're asked to do is compute the derivative dy dx. And we can do that, but first, we're going to apply the natural logarithm to both sides. On the left, we'll have the natural logarithm of y, and on the right, we're going to have the natural logarithm of this entire expression. So it's the square root of x times sine of x quantity squared, like so, and then we're dividing by this polynomial, 1 plus 3x squared plus x to the 4. And again, this is a very complicated expression, but we can use the properties of logarithm to simplify this by a significant amount. So this is going to be equal to, well, we're going to just convert all of the multiplication into addition and then the division into subtraction. Or maybe we'll do the division first. So we'll have ln of the square root of x times sine of x quantity squared, and then we're turning the division into subtraction, ln of 1 plus 3x squared plus x to the 4. Now there's not really anything we can do with that term at the moment, so we're just going to leave that alone, but we're going to simplify this one quite a bit. So this is going to be using the property that turns multiplication into addition. This is going to be ln of the square root of x plus ln of sine of x quantity squared. And maybe I'll just use parentheses here around the logarithm, like so. And then we're going to leave this last logarithm alone for the time being. Not going to really do anything to it. And then we're just going to rewrite this as ln of x to the 1 half plus ln, and again we have sine x squared minus ln of this polynomial, 1 plus 3x squared plus x to the 4. And we're going to use our property of logarithms that allows us to take the exponents out. So we're going to take the 1 half in front and the 2 in front. And so then we'll have that the natural logarithm of y is equal to 1 half ln of x plus 2 ln of sine of x minus ln of 1 plus 3x squared plus x to the 4. Now the thing that we're actually interested in, the thing that we're looking for, is the derivative of y. And here on the left we don't have y, we have the natural logarithm of y. However, we can differentiate using implicit differentiation. So we'll have the derivative with respect to x of ln of y is going to equal the derivative with respect to x of all of these terms here. So let's just quickly write them down. Minus ln of this polynomial, like so. And this is actually going to make our work a lot easier. On the left, we have the derivative of ln of y, and you might think, but don't we want the derivative of y? Well, using the chain rule, we're going to get the derivative of y, because the derivative of ln of y with respect to x, well, the derivative of ln of anything is 1 over that thing times the derivative of whatever's inside, which is dy dx. And that's the thing that we're looking for. Now on the right, we can just easily differentiate all of this stuff using the chain rule. So we have 1/2 times the derivative of ln of x is 1 over x, plus 2 times the derivative of ln of a thing is 1 over that thing. But then we have to multiply by the derivative of whatever that thing is. But we know what the derivative of sine is. It's cosine. And then we have minus the derivative of ln of a thing, again, is 1 over that thing, so 1 over that polynomial, times the derivative with respect to x of that polynomial, 1 plus 3x squared plus x to the 4th. And again, we know how to compute the derivatives of polynomials. That's going to be 0 plus 6x plus 4x cubed. So if we put all of this together, we have 1 over y times dy dx is equal to 1 over 2x plus 2 times cosine of x over sine of x, which is cotangent if you want to write it that way, minus 6x plus 4x cubed divided by 1 plus 3x squared plus x to the 4. And this is almost our answer. What we want is dy dx, so you just have to multiply this y over to the other side, and then you'll have that dy dx is equal to y times all of this stuff. And again, you could write this as cotangent, but I'll just leave it as cosine over sine, minus 6x plus 4x cubed over 1 plus 3x squared plus x to the 4th. And of course you have that y there, but we need to just remind ourselves what y was. In the very beginning, we knew what y was. Y was equal to this expression, the square root of x times sine of x quantity squared divided by that polynomial, 1 plus 3x squared plus x to the 4. So now we can just plug that back in, and we'll have that dy dx is equal to the square root of x times sine of x quantity squared over that polynomial, which was 1 plus 3x squared plus x to the 4. And all of this is times everything in the brackets. 1 over 2x plus 2 cosine x over sine of x minus 6x plus 4x cubed over that same polynomial. 1 plus 3x squared plus x to the 4. And if we just fix that x cubed so it looks more like a 3 there, there's our answer. It was still quite a bit of work, but it was a lot easier than just doing it directly. We can use this method of logarithmic differentiation to compute the derivatives of very exotic objects like x raised to the cosine x. So let's do it exactly the same way. So we start by letting y be equal to x raised to the cosine of x. And the issue here is that we have an x in the base, but there's also a function of x in the exponent. So what we're going to do is try to get the exponent out of the exponent by using a logarithm. So we just use ln on both sides. So we have ln of y is equal to ln of x raised to the cosine of x. And now we use the properties of logarithm that allow us to take the exponents out and just put them in front. So we'll have ln of y is equal to cosine of x times ln of x. And now we just apply the derivative to both sides. So the derivative with respect to x on the left, that's the derivative with respect to x of ln of y, is equal to the derivative with respect to x of cosine of x times ln of x. On the left, we use the chain rule, so it's the derivative of ln of a thing, so that's going to be 1 over that thing, times the derivative of that thing with respect to x. And on the right, we're going to use the product rule. And that gives us the derivative of the first, so the derivative of cosine, derivative of the first, times the second, plus the first, times the derivative of the second. And we know these derivatives. The derivative of cosine of x is the opposite of sine of x, and the derivative of the natural logarithm of x with respect to x is 1 over x. So that tells us that 1 over y times dy dx is equal to the opposite of sine of x times ln of x plus cosine of x over x. The thing we're trying to find is dy dx. That's our objective. So we just multiply this y over to the other side, and then we'll have that dy dx is equal to y times all of this stuff, minus sine of x ln of x plus cosine of x over x. And then we just remind ourselves what y was. Y is x to the cosine x. Y is equal to x raised to the cosine of x. So now you just plug that in and you have your answer. Dy dx is equal to y, which is x cosine of x, times everything else, minus sine of x ln of x plus cosine of x over x, like so. And that's our answer. That's the derivative. This expression is the derivative with respect to x of x raised to the cosine of x. Now this function is an interesting function, and we can graph it using a computer. And you can see it here, the graph of y equals x raised to the cosine of x. As our last example, we'll prove this limit theorem, which recognizes e as a limit, and the limit in question is the limit as x goes to 0 of 1 plus x raised to the 1 over x. So this limit is e. So how are we going to show that? We're going to start in a way that maybe is not obvious. We're going to start by letting f at x equal the natural logarithm of x. And what we're going to do is we're going to compute f prime evaluated at 1. Now this is something we can do easily enough because we know that f prime of x is equal to 1 over x. So that tells us that f prime of 1 is just simply 1 over 1, which is 1. But let's do it now using, so let's use the limit definition of the derivative. Using the limit definition, we have that f prime of 1 is equal to the limit as h goes to 0 of f at 1 plus h minus f at 1 divided by h. Okay, so this is the limit as h goes to 0 of, well, f at 1 plus h, that's ln of 1 plus h minus ln of 1 over h. Well, of course, ln of 1, that's just equal to 0. So that tells us that f prime of 1 is equal to the limit as h goes to 0 of ln of 1 plus h over h. Okay, so how's this going to help us? Well, we're going to just rewrite this slightly. So this is going to be equal to the limit as h goes to 0 of 1 over h times ln of 1 plus h, like so. So now we're going to use the property of logarithms that we've been using, but we're going to use it backwards. We're going to take this number 1 over h, which is in front of the logarithm, and we're going to put it as an exponent on this 1 plus h. So we're going to just put little brackets around this, and then we're going to just take this 1 plus h and put it over here. So that tells us that f prime of 1 is equal to the limit as h goes to 0 of ln of 1 plus h raised to the 1 over h. And I said we were going to use brackets, so let's just put a bracket here, like that. We know that this is equal to 1. But 1 is equal to ln of e. So what we have here is that the limit as h goes to 0 of ln of 1 plus h to the 1 over h is equal to ln of e. The natural logarithm is continuous on its domain, so in particular what that means is that the limit of this function as h approaches 0 is going to exist and be equal to ln of the limit as h goes to 0 of whatever was inside, 1 plus h to the 1 over h. And this is equal to ln of e. Well, the only way that this can happen, since the natural logarithm function is a one-to-one function, is if the arguments are the same. So if this limit as h goes to 0 of 1 plus h to the 1 over h is equal to e. And so what does that tell us? The limit as h goes to 0 of 1 plus h to the 1 over h is equal to e. And that's really what we wanted to prove. We can just change h to x and we'll get the original statement. The limit as h goes to, well, we're going to change h to x. So as x goes to 0 of 1 plus x to the 1 over x is equal to e. And that's exactly what we claimed. Now, another change that you can make is you can change x to 1 over n. And then what you're going to end up with is the limit as 1 over n goes to 0, or as n goes to infinity, of 1 plus 1 over n raised to the n is also equal to e. And this is sometimes how e is defined. And we were able to show these limits by looking at the derivative of the natural logarithm, which probably is a little unexpected because there's nothing in these limits that makes it seem like a natural logarithm is involved, but it was precisely computing the derivative of the natural logarithm that led us to this limit.